Okay, our next topic is about planes. And for this topic, it is quite important to understand the span notation as explained in the last video. And an important point that I will explain is that the span is very correlated with the origin for the topics we'll discuss. So just keep that in mind and we'll come back to it. So firstly, we talked about lines in vector representation where we had a v and a w in Rn, and we had an a or any variable you want to assign in R, and the vector, let's say the line is L, and that's obviously in Rn as well, and it's in the form of v plus w times a. Now in here, v gives us our starting point, and w gives us our direction vector, and a basically makes it so that it is aligned, since we just infinitely have the possibilities of different scales of w. Now planes, these are different, they're a different concept than lines. And the most basic plane we can have is by adding another variable to the line equation. Let's say a plane is denoted by p. Let's also introduce another variable. Let's say b is in the real numbers as well. Now this plane is going to be the product of b and the vector v plus product of a and the vector w. Now this plane, just like the line, they're both going to be in Rn. Rn meaning they'll always be in the same n of v and w. And same with lines. So when I say Rn means they're all gonna have the same, because this is just scalar multiplication and then addition. It doesn't change anything with n. Now, span notation, our first time of seeing it here is going to be span of v and w. And that's how span notation is useful in this case. And obviously I'll write this once, but we know that this just means it denotes a set such that we already used a and b, so let's use a and b again. V plus bw, and you can use colons to specify the function. Oh, I wrote it differently this time. It doesn't matter, but I'll change it so it's consistent. And a, b, and real numbers. Now this set, remember, it defines a line, but this line is defined by the terminal points of these vectors, meaning where they point at in relation to the origin. So the terminal point is going to be where this arrow is for any vector. Now this is a basic plane. I want you to remember that in here, the vector v and the vector w impose direction. It's almost like a Cartesian plane of its own, a plot. So if you had a Cartesian plane over here, we're going to use this to show the vectors. Now, by having these scalar coefficients b and a in the real numbers, we're defining all sorts of directions. Say v is this vector and w is this vector right here. This is more, I'm drawing it more 2D in this case, but it doesn't really matter. Now, by adding these coefficients, we're creating a whole or a plane of different terminal points. So v and w are obviously in this plane, right? Because we can have b equals 1, a equals 0, and vice versa. Now, we can also have b is 1 and a is 1 as well. Then we would use vector addition. And that would give us a point over here, which is this point in the origin. Now, if we'd have 2w, then we're going to put another w here. It's going to give us this point. And this is going to define basically everything here. It's going to be enormous and infinite. But that is what a plane is. That is what we define as a plane. Now, of course, there are some exceptions. This is not always going to lead to a plane. Now, you might be wondering, what are those exceptions? Well, some might be obvious, some might not be as obvious. Now, the first obvious thing is, well, if v or w is the zero vector, that is going to give us, if they're not both the zero vector, then we're basically going to get the span of one of these vectors. I can just say v or w. This is not proper notation, but it's just for the analogy. And this is just going to give us a line through the origin. This is just a line through the origin. It's your vector, and then you can have many different scalar constants, and it's going to extend here, go negative if you have a negative coefficient. So remember that you're not going to get a plane if one of these are the zero vector. Another way this might happen, well, on the same concept, is if a or b can be 0. That's a mistake by me. That other way is if either of these are related. So we can just define it by saying v is not equal to a scalar, say a again, but they're obviously different a's. So these are not related for any a in the real numbers. And this is important. Why, you might ask? Well, if v can be represented as a and w, then essentially when we have our supposed plane equation, we're going to have aw plus, say, another coefficient bw, which is just a plus b times w. Well, you might recall or might not recall, but here a plus b is a real number. So this is basically a line through the origin with the scaling, right? A plus b can be just set to another real number defined by like a variable c or something. So yeah, so that's basically how we can represent our basic spans and things that affect these. Now, we would like to extend this idea to define an actual plane, a more progressive version of the plane. This is going to be our definition of the plane. Now, a plane is actually, first we need to set our different variables that we want to use in our equations. We're going to have v, w, and a t, which are in Rn. We're also going to define a and b and r. Now the plane equation is going to be a t plus an aw plus abv. Now, all the planes we've discussed until now do fit under this category if t is the zero vector, or if t is a multiple of w, the vector w, or the vector v. And if you realized with the explanation of a line and all these different concepts, right, of how this plane can be transformed into a line, well, then this plane can also be transformed into the old version of our plane. And these planes, with the constraints I mentioned, say t is the zero vector, these are actually planes that go through the origin. So there are more ways to get these planes that go through the origin. And how, you may ask? Well, as I just said, if t is the zero vector, or t is in the span of w and v. So this is a span together. Now, why would it be so? Well, because t is in the span of aw and bv. Well, we can always get to the origin by how? Well, we're saying that there is one element, a and b, there are two elements, a and b, that will equal t at some point. That's what the span definition is. And if we're able to get the zero vector, well then our plane is going through the origin. Keep that in mind. It's going through the origin if we get a zero vector. Now, there's another small concept that may be useful, and this is if we have three collinear points on a plane. Now, why would we need three collinear points on the plane, and what are collinear points, you may ask? So firstly, collinear points are points that can't all be connected using one straight line. So, using our vectors v, w, and t, if I have a vector v over here, and if I have any other vector, any other vector, say w is over here, I can connect them with a line, Any two vectors can be connected with a line. Now, if I have another vector t, it can either be on this line, somehow, there are many ways you can probably do that, or it can be away from this line. And by it being away from this line, is where we can actually have three collinear points. And what's so special about these collinear points is these points can create a plane. we can assign one of these vectors as our t vector. So I guess it's most logical to make the t vector t, right? So let's say our t vector is t. Well, then we can have w and v kind of attached to these, right? And in this way, notice our plane is not on the origin. This is not going to be on the origin. Unless, of course, we meet the specific qualities that I mentioned previously. Now, how are these points going to be related on the plane if we select t as the point t in this case? Well, you need to now notice that there is this is actually pretty easy to represent. But what if we wanted to, if you wanted to represent this as basically this equation. So I don't know why I was wasting time with that. Okay, so what is useful about having these? Well, we can define, if we have these three collinear points, then we can actually define a plane that contains all of these points. How can we do that? Well, notice that we have these lines that connect these vectors up. And these lines are tangential to each other. They're tangential to each other and they connect each other up. So by connecting each other up, it's in a way, when we do create an equation for this, we're gonna have these two direction vectors right here. This is going to be a direction vector. This is going to be a direction vector. Then remember, if we have two vectors, say AV and BW, if we have two direction vectors, we can create a plane using them. And this plane is essentially, in this case, V is our starting point. But we can also make any of them our starting point. But then we would, in a way, need our direction vectors to stem out of this, the terminal point of the starting vector. So just for demonstration purposes, I'm going to slightly erase this so I can quickly show why we can make it any way we want. Say V is here, excuse my drawings. Now we can connect T and V together and a V and T together. Now T is the starting point. And that's basically how you do it. Now, what are these points that join these things together? Well, this line over here is T minus W. You can try that for yourself, but that is the line TW because I can just do my basic T minus W's here, and the line goes here to this tip, and that is going to be the point since it's pointing there. And if it was the other way, then it would be negative t minus w, but it's not. And this other point, basically, I told you the concept, so that is t minus v. Now, we can define our plane now. We have t as the starting vector, and then we can use constants. So now we've managed to define these vectors in a way so that we can have a plane that goes through every one of them. Now, oh yeah, by the way, it doesn't even actually matter if these are the wrong way around or right way around, because it's gonna create the same plane. You can double check that if you want to create the plane with these lines pointing in the directions I mentioned. Now the scalar equation of a plane. So recall when we did the cross product of two vectors v and w. Say v is here, w is here. Well, we've defined it only in R3, our cross product. So this equation called the scalar equation is also only going to be in R3. Now we call that let's say that n is equal to the cross product of v and w, and v and w are in R3, and n also has to be in R3. Okay. And n is orthogonal to both v and w. Now, v and w, let me put this on an actual Cartesian plane. Sorry for not drawing the y-axis and the x-axis, like labeling them. We're going to get this point over here, okay? This one vector. Now, what is important about this vector? Well, v and w are direction vectors in our plane. If we have this vector, we call it the normal. Okay, we call it a normal vector to the plane, because it's normal to the plane. So it's a normal. Now, what is so important? Well, v and w are direction vectors. But in our equation, we have t is equal to t plus av plus bw, right? There's going to be a t vector that determines where our plane starts. It could be at the using the zero vector or the multiple, as I explained, and that would still make a valid plane, and that would be through the origin. But that's not what's special about these. The thing that's special about these vectors, about this normal, is that it's always going to be normal to any point on the plane. If I give you any point here, it's going to be normal to it. On the plane, the point must be on the plane. But actually, I might have made it a bit I might have mentioned this a bit incorrectly. Actually, it would be a normal to any vector that is also tangential to the plane, like v and w, and not necessarily any vector on the plane, because our plane is defined by terminal points that stem from the origin, so those are going to be vectors in different directions. So ignore that, and I will explain how this works. So let's say I don't know how to draw this in 3D. let's just define a v and a w. Let's say it goes to the origin for simplicity's sakes. Now, if it goes to the origin, our v is going to create this huge, like, infinite plane over here. Now, in this case, yes, every vector here that results from it, since it's to the origin, and is going to be normal to it. But if it starts off somewhere else with a t that is not the zero vector or a multiple of either of those vectors, then we're gonna have our v and w kind of here, but these aren't the proper points of v or w. Now, I might have not mentioned this, but v and w don't have to be on the plane, because if we set a and b to be 0, you're going to get the vector t, which is not the 0 vector. So if we get this huge plane, I'm trying to do it kind of 3D-ish, not very good at it. So any vector that is like kind of like this on the plane, call it tangential to the plane, because when we bring it down to the origin, these vectors, remember, we can move the vectors wherever we want, but they're defined by their terminal points based only when their initial point is at the origin. So these are tangential to the plane, and the vector n is normal to all of these vectors. So why is this useful? Now, since I've already mentioned, we're just going to write the constraints. We're going to have here v is not equal to 0, w is not equal to 0, and w is not equal to n and v. And this is all in R3, just to remind you guys. So, say we're given a point, 2 points on the vector. We're given our plane equation. Our plane is equal to t plus a v plus b w. And we're also given another point on the plane, vector x. Now, this is a proper point on the plane. This is not one of those tangential vectors. Then say we have a t that goes here, right? Now, I don't think I need to mention this anymore. We can have our v and w as direction vectors. It might seem like my drawing is 2D, but I'm trying my best to make it look like a 3D diagram. And we're gonna have a plane defined by this, right? But if I give you another point, say here in this plane, labeled x, it's a vector, then x is not what's it called, orthogonal to the normal vector. But we have something that is. And that's gonna be this vector right here. This vector over here. Or the vector that goes in the opposite direction, minus of this vector. Now what is this vector? Well, if I were to, I'll just tell you guys what it is. It's just x minus t. You can figure that out yourself using probably the parallelogram law, however you want. Now, this gives us an equation, right? So, since we're orthogonal to all these different points, all these different vectors that are tangential to the plane, well, the dot product of n, and for this example, we'll say x minus t, where x is any vector on the plane, This is firstly, remember that it's a cross product, which is v cross w, and this is the dot product of x minus t, and this is equal to 0. It's orthogonal. Remember, it's 0 if it's orthogonal. This is useful because if we're given an equation, well, we're going to know this cross product because we'll know the vectors v and w. We will also know what t is. And this is going to give us an expression with 3 different variables, so x, y, and z. And they're gonna have coefficients, let's say ABC. This is going to be equal to 0. And this is actually a plane. Algebraically, this is actually a plane. You can try and graph them on a 3D calculator. It might be helpful. Also, if the plane goes to the origin, then recall that we're going to get a vector like this. O, that's the origin, say V, we have a W. We're going to get this normal line, normal vector. Well, in this case, n is normal to any vector in this plane, correct? But any vector in this plane is essentially what? Has any vector using your equation, of course. And it can also include p, since if it goes to the origin, p is related. So n dot p will also be 0. And this might be useful if you wanted to find p for some reason. And yeah, also n is dot minus p is also 0. It's important and might be useful because we always know what n is in these cases. Now I hope this helps, and I'll probably do some videos where I solve some questions, so it might be useful. Thank you.